So in this video we want to develop a method for finding a normal vector to a surface. So we can have a surface in three-dimensional space either explicitly defined like this, z equals some function of x and y, or we can have a surface in three-dimensional space implicitly defined as c equals f of x, y, z. And just as a reminder, if we're saying that we're explicitly defined, that means we've been able to isolate the z. So for example, the surface z equals x squared minus y squared is explicit because we've been able to explicitly isolate z, and z doesn't show up anywhere on the right hand side, and on the left hand side it's to the first power. So we explicitly were able to solve for z. So that would be this case here. And if it's been implicitly defined, we might have something like 9 equals x squared plus y squared plus z squared, where this stuff here is our f of x, y, z, but the surface as a whole isn't a function, and in fact this is a sphere of radius 3. So we would say here z is implicitly defined because we can't solve explicitly for z. So there's two ways that a surface in 3 space can be described, either explicitly or implicitly. The process for developing a normal vector is the same in either case. And then remember, a normal vector just means it's perpendicular to the surface. So if I want it to be normal to the surface, I'm saying I want it to be perpendicular to the surface. So here's the idea. Suppose I have some surface in three-dimensional space. Who knows what it is? It doesn't matter. Even if I draw it poorly, it doesn't matter. So some surface in three-dimensional space. Let's say there's an arbitrary point on the surface right here. We're going to say that arbitrary point is the point x naught, y naught, z naught. And at the point x naught, y naught, z naught, we want to find a vector that is normal to the surface at that point. And so normal means it's going to hit the surface at a 90-degree angle, or it's going to be perpendicular to the surface. The surface itself actually has a tangent plane at that point, and so this normal vector is going to be perpendicular to the plane that is tangent to the surface at the point x naught, y naught, z naught. So here's the basic idea. Either way we have described our surface, whether it's a function or a relation, we can either subtract z or subtract this stuff c from both sides and get 0 equals either f of x, y, z minus c, or we can get 0 equals f of x, y minus z. In either case, we wind up with some function of 3 variables right here. So I'm going to call him big F. I get a function f of x, y, z of 3 variables in either case. And when I do this, there's three things that I know. I know that in both cases, f of x, y, z is equal to 0, which means that the rate of change of big F at this point is going to be equal to 0. Because the function is equal to a constant, the rate of change of a constant is 0. And either f of x, y, z is equal to f of x, y minus z, or big F of x, y, z is equal to little f of x, y, z minus c. One of these two things is true. And so the idea is that the surface at the point x naught, y naught, z naught, there's going to be infinitely many curves on the surface that pass through and contain that point x naught, y naught, z naught. Parameterize one of those. So let me take one of those infinitely many curves on the surface. We'll call the surface S. One of the infinitely many curves on the surface I can draw through this point and parameterize it. So I'll look at the side view of him. So here's a side view of one of the infinitely many curves. Here's that point x naught, y naught, z naught on the surface, and let's parameterize this curve in this way. we're going to parameterize it so that the curve is described by r of t. So we're going to parameterize it as a function of t. So it's going to be parameterized as x of t, y of t, and z of t. And we parameterize it in such a way that when we plug in t naught, we get the point x naught, y naught, z naught. So we get x naught, y naught, z naught. So if we take the derivative of r, so let's say we have r prime of t, which is just going to be the derivative of the components, x prime of t, y prime of t, z prime of t, then r prime at t naught, or at the point x naught, y naught, z naught, r prime at t naught is just going to be tangent to the curve. The derivative of the curve is tangent to the curve. So r prime at t naught is tangent to the curve at the point x naught, y naught, z naught. So the next thing that I want to do is, if I parameterized x, y, and z along this curve, and I think about this function here being f of x of t, y of t, z of t, using the parameterized x, y, and z along this curve which lies on the surface, then I know that I can calculate the rate of change df dt using the chain rule. So the chain rule says that the derivative is going to be the partial derivative of f with respect to x times dx dt, which is just x prime of t, plus then you have to take the partial derivative of f with respect to y and multiply by dy dt, plus you need to take the partial derivative of f with respect to z times dz dt. And dz dt is just z prime of t, dy dt is just y prime of t, and dx dt is just x prime of t. And so we can actually write this as a dot product. Partial f, partial x, our shorthand is f sub x. Our shorthand for partial f, partial y is just f sub y. The shorthand for partial f, partial z is just f sub z, the partial derivative with respect to z. And we're really dotting it with the vector x prime, y prime, z prime, which is just this r prime of t vector right here. So r prime of t. So the idea is, if we want to know the rate of change of f with respect to t at this point x naught, y naught, z naught, we're really looking for the rate of change of f with respect to t at t naught, which means because r of t naught is x naught, y naught, z naught, that means calculate the partial derivatives at the point x naught, y naught, z naught, and then replace t in r prime of t with r prime of t naught, the vector that is tangent to the surface, which means it's tangent to this curve, which means it's tangent to the surface that we have. And then I want to recognize, because f of x, y, z is always equal to 0, then f of x naught, y naught, z naught is equal to 0, which means the derivative of f with respect to t at t naught has to be 0. The function f is a constant, which means its derivative is 0. And now I have the dot product of two vectors equaling 0, but this vector is tangent to the curve, which means this vector must be perpendicular to the curve. And if it's perpendicular to the curve, then it's perpendicular to the entire surface. So now I have a vector right here that is perpendicular to my surface S at any x naught, y naught, z naught. And what I want to recognize is that this right here is how we defined in the previous homework the gradient of a function. The gradient of a function is just the vector that contains the partial derivatives as its components. So the x component is the partial derivative with respect to x. The y component is partial derivative with respect to y. And the z component is the partial derivative with respect to z. And then finally, to wrap this all up, if we're in the special case where the function's been explicitly defined like this simplifies even more. So in the explicit case, explicitly defined case where we have z has been isolated as a function of x and y, then now I can think about what does the gradient of my big F equal here. Well, there's no z in the f of xy piece, and there's no y attached to the z. There's no z in the f of xy piece, and there's no x attached to the z. So the derivative of big F with respect to x is just going to be the derivative of little f with respect to x. The derivative of big F with respect to y is just going to be the derivative of little f with respect to y. And the derivative of big F is just going to be the derivative of minus z with respect to z, which is just -1. So the idea is we always take and create a function big F by subtracting the relevant portion from both sides and getting the function big F equal to 0. The gradient of that big F is always perpendicular to the original surface. The gradient of big F is always perpendicular to the original surface. And in the special case where we have an explicitly defined function, we can calculate that gradient very easily as the partial with respect to the original f of xy, with respect to x, the partial with respect to y of the original f of xy, and a -1 in the z component.